So let's dive into it. So this is the outline of my talk. I'm going to hopefully give you a pedagogical discussion about nuclear properties and the R process so that we are all on the same page about what does the R process mean, what are sort of the restrictions in order to be produced, and what are the abundance patterns related to neutron capture. And they'll tell you a little bit about what do we know about the R process from high-resolution abundance observations in stars, and a significant fraction of our insights of nucleosynthesis come from the study of basically nearby and halo stars. And they'll tell you about neutron star mergers and how they are able to synthesize the R process, and really focusing on what are the observational signatures of how we can ultimately see these events, so that you kind of get an understanding of the groundwork that took place before the detection of the gravitational wave signal, especially GW 170817. So I'll tell you a little bit about the lessons learned from that, and of course that's been our only event so far in which we have detected both. And I'll tell you a little bit about the challenges of why is the case that continues to be currently the only event. And then even if you don't care about our process nucleosynthesis or gold and platinum, hopefully I will convince you that our process nucleosynthesis is incredibly essential for us to be here. So I'll give you some arguments about how planet habitability is intimately linked to the production of our process nucleosynthesis, and I'll give you some insights about chemical evolution, and how ultimately the imprints of the rarity of these events is actually imprinted in the basically variations of our process nucleosynthesis in stars in our Milky Way halo. Okay, so as you know, in this audience, I don't have to tell you, for astronomers, this is our periodic table. This is the abundance pattern of the sun. And there's a few things that you can immediately highlight here, that abundance peaks actually correlate with nuclear structure. So what I'm showing you there are the close proton and neutron shells. And as you can see, they clearly correlate with abundance peaks. We'll talk a little bit about the odd, even asymmetries that we see there. And the things that I want you to focus on is that beyond the iron group, as you know, charge reactions are incredibly difficult to basically give rise to elements more heavy than iron, both because the Coulomb barrier increases drastically, and ultimately because iron is the most bound nuclei in the universe, that you require basically the capture of neutrons to make elements above the iron peak. And then the other thing that you see is that stability requires a larger number of neutrons in order to create stable elements. So you can see here something like lead, which is doubly magical, which is basically has a proton closed shell, and a neutron closed shell has a significantly large fraction of neutrons. Yeah? So what I'm going to try to guide you is I'm going to give you intuition as to particularly the peaks in the R process. So you can see here this peak. At first sight, these peaks don't seem to correlate with nuclear structure, and ultimately I'm going to give you an insight that they do correlate with nuclear structure, but they're actually synthesized very far away from equilibrium. And when we think about primarily avenues for this, as you know, of course, Big Bang gave us primarily hydrogen and helium, nuclear burning. And then neutron capture is responsible for about almost 95% of all the nucleus above the iron peak. Now, when you capture a neutron, you become radioactive and you beta decay. Yeah? So we call the slow process, or S process, if you capture neutrons slowly compared to the decay. So you're very, very close to the beta stability, and I'll show you that in detail. And that gives rise to that abundance pattern that you see, the S process. And then if you capture neutrons rapidly, the R process, before they beta decay, gives rise to the R process abundance pattern. So what I'm going to try to give you an intuition is this, primarily focusing on these first three peaks: first peak, second peak, and third peak. And I'm going to give you some intuition as to why the R process has the peaks shifted to the left. Okay. And in order to do this, I'm going to show you this beautiful diagram from Chris Newton, in which we're highlighting here proton number as a function of neutron number. If I capture a neutron and I beta decay, I move in this plane. The first thing that I want to highlight are the stable nuclei. So this is where stable nuclei live, in black. And if I move away from stability, imagine that I'm a nuclei here, and I actually start to reduce the number of protons, and I move down into this regime, the lifetime of these nuclei becomes very, very short. This is the beta time scale. Yeah? So nuclei that are very, very kind of far from stability only are stable for milliseconds, as you can see. So it's going to become a really crucial feature for us. Why? Because if you produce, an R process nucleosynthetic pathway with separation energies of a few MeV, which is highlighted here, you can see you need to basically capture neutrons very, very far from stability. So the simple argument that was made was that if you look at the R process pathway and you look at the time scale for decay, which are tens of milliseconds, you can immediately say, well, what is the only stable object in the universe whose dynamical time scale is of the order of tens of milliseconds? And the answer is a neutron star. So the time scales for the R process can only be achieved close to a neutron star. So either when two neutron stars merge or when a neutron star is actually formed, simply from the time scale argument. In addition to this, we see these closed neutron shells, which basically highlight nuclear stability. And in particular, I want to highlight this as the first, second, and third closed neutron shells, which these so-called magic numbers. So what happens in those closed neutron shells? In order to illustrate this, I'm going to show you the neutron capture cross-section for an S process pathway, but this is fairly universal from the Clayton handbook. The way that I want you to think about this is imagine that you have this flow of neutrons that you're capturing. And at these, particularly at the magic numbers, the first thing that you notice here is that odd mass numbers tend to have higher cross-section than even nuclei. So remember the odd-even asymmetry in the abundance pattern. That's deeply related to the change in cross-section. But if you look at the magic numbers, you see the substantial lowering of the cross-section in these magic numbers. Why that's the case? Because of course these nuclei do not want to capture neutrons. They're stable. Yeah. So the way that you can think about this, you can think about that as a flow of neutrons, and ultimately these are caustics in the flow. Yeah. You basically get a pileup at that particular magic number. Imagine that you have a highway of neutrons, and then you have a kind of an accident, a pileup, then the cars will basically pile up, and that will give rise to an abundance peak. So as a result, abundance anti-correlate with neutron capture cross-sections. Okay, and that's incredibly important to build our intuition about these three peaks. So imagine that you're capturing neutrons slowly, you're moving very close to a stability, and then I get my first stagnation point here. I get my first peak. I continue to capture neutrons. I get my second peak. I continue, and I get the third peak. And that gives rise to the first, second, and third peak in the S process. And because you're doing it close, to equilibrium, basically the number of neutrons is preserved. So those are clearly shown in the abundance pattern. But if you do that far away from equilibrium in the R process, you get your first peak, your second peak, and your third peak, but then they're not stable, and then you beta decay. So the peaks basically get projected to the left. So you get the first peak, second peak, and third peak as you decay back to stability. And that decay back to stability is ultimately what's going to power the Lie curve of these events, and we'll talk about that. So as a result, when we looked at the abundance pattern, you clearly see, you have the first magic number of the S process, the second, and the third, and you clearly see the shift to the left of the R process. So yes, they are related to nuclear stability, but of course they've forgotten about the neutron number at the time of capture because they decay back to stability. You can ask me more about these rare earth peak and how it's actually made. But I'm highlighting here europium. And the reason for that is europium has an oscillation strength that permits us to see basically our process content of stars, and is actually used as the tracer of our process. And something that it's incredibly important to keep in mind is that about half the elements are made through the S process, half the elements are made through the R process, but a particular element can be made by both. You can see here lead is basically, at the few percent level, also made by the R process. My favorite peak is primarily an R process peak, gold and platinum. That's primarily basically rapid neutron capture, as it is the rare earth peak where europium sits. So what do we know about our process in stars? So what I'm showing you here is the so-called Sneeden star in honor of Chris Sneeden, which it has in relative proportions the highest gold content of any star. Yeah, it's a low metallicity star. So what do we know? We know, as you know, in astronomy, we're plotting abundances in terms of the sun. So we live at 0, 0. The first thing that you realize is that there's large abundance variations for stars at similar iron abundances, and I'll give you an insight as to why that takes place. This has to do with mixing and chemical evolution and the rate of injection being small. But more importantly, I just wanted to kind of highlight the R process in these two stars. So this is the Sneeden star, so of course its relative R process abundance is the highest. And this is a star that has similar iron abundance, but it has very little R process content. And if you look at a high resolution spectra, if we focus, say, for example, in the calcium lines, the depth of the calcium lines are similar, but if you look at the europium lines, you can see the difference in R process content. So you have these very, very large variations in R process. And as I also was highlighted there, only a small fraction of low metallicity stars have R process to a detectable level. Another thing that it's incredibly important is that the R process pattern, particularly the heavy R process, that is between the second and third peak, is incredibly robust. What you look at here is basically stars at low metallicity, and that they have been displayed in the y-axis arbitrarily, so that you can see that the R process abundance pattern of the sun fits incredibly well their pattern distribution. So what does that mean? That whatever mechanism you come up that builds the R process has been operated in an incredibly robust way since the beginning of time. Not only that nucleosynthetically, if you change the initial conditions slightly, you have to converge to a pattern that is similar. No? So that puts some stringent constraints in order to actually make sure that we get these robustness of the R process. Now, this is kind of an order of magnitude estimate that I wanted to leave you with to give you some intuition. If you want to explain the total R process content of stars in the Milky Way, you need to produce about 10 to the minus 7 solar masses per year of R process. So this is for a Milky Way-like galaxy, which you're producing about 1 solar mass per year of new stars. So you need basically 1 part in 10 million or so of solar masses per year. And then if you do the integral and the age of the Milky Way, you get that in total you have about 10,000 solar masses of R process in the Milky Way. Yeah, that gives you the order of magnitude. So when we thought about the two mechanisms to produce the R process, core collapse supernova happen once every 100 years. So in order to get to these 10 to the minus 7 magic number, you need to produce about 10 to the minus 5 solar masses per event. While neutron star mergers, of course, you have to produce 2 neutron stars, and then you have to assemble them for them to be close enough to merge in less than than the age of the universe. So this is much rarer event, and it's about 1 every 10 to the 5 years. That means that if you want a viable R-process nucleosynthetic pathway, neutron star mergers have to produce about 1% of a solar mass per event. Yeah. Now, there's a simple estimate that can be made of what is the minimum amount of R-process per event that you need to produce. And this comes because low metallicity stars, we think, were actually enriched by basically one event. Yeah? So if you think about, if I have an explosion and I produce freshly synthesized material, you say, what is the fastest or the most effective way for me to turn that into stars? And the first requirement is that you have to cool that material. You have to get to the cooling phase, and therefore you can calculate, okay, what is the cooling phase of that explosion, how much material I have, and that gives me basically a strong constraint on what is the minimum amount of metals that I have to produce within that cooling mass in order to explain the abundances that I see. Of course, if you sweep significantly more hydrogen, you have to put significantly more of those metals. So it gives you a strict lower limit. And when you do that for low metallicity stars, you basically can rule out core collapse supernova. Standard core collapse supernova do not produce enough of this material. And if you look at something like this Needham star, that's what gives you the strongest constraint. And it tells you that at a minimum, per event, you have to produce about 10 to the minus 3 solar masses. Yeah. So beautifully, just by actually looking at our process nucleosynthesis, you know that the production of what we call the heavy R process, which is the second and third peak, has to operate incredibly robustly. So we have to basically be able to obtain the solar abundance pattern very effectively. And it has to be operating at a drastically reduced rate when compared to core collapse supernovae. Yeah? That means that it's an incredibly rare event. And as a result of the rarity, you see these large RMS fluctuations of our process content. And I'll give you some guide as to how that arises when we think about chemical evolution. So there are many avenues when two neutron stars merge to actually be able to eject material from the system, which is intimately linked to basically heating the material. There's the tidal tail ejecta, which I will primarily concentrate because it's the simplest and most robust pathway to the R process. There's this so-called squeeze polar ejecta when the two neutron star touches and there's material, a small amount of material that gets heated above the escape velocity in the poles and it's able to escape. And we actually think that the larger reservoir actually takes place when the two neutron stars actually collapse into a black hole and you form an accretion disk. And this is probably the largest mass reservoir where viscously, through viscous winds, you can get significant amount of material. Now, particularly this pathway is much more complicated because you have to do the neutrino transport. So what I'm going to guide you through is the nucleosynthetic pathway for the tidal tail ejecta, which actually doesn't require any neutrino irradiation, and neutrinos play basically a non-important role. So this field has evolved dramatically since I was a PhD student here, where we are now doing GR, MHD, neutrino transport calculations. But just for the sake of history, I'm going to just show you the calculation I ran for my PhD. So these are two equal neutron stars, equal mass, so they're basically symmetric. You get mass shredding in the outer Lagrangian points, and about 1% of a solar mass of material gets above the escape velocity. And here I think the outer Lagrangian points have escape velocity of about 20% of the speed of light, and you're able to basically lift of the order of about 1% of a solar mass. So what I want to guide you through is we're going to center ourselves in the tidal tails, and we're going to follow the nuclear evolution of the tidal tails so that you see how the R process is formed in real time. So hopefully this movie is a little slow, so if not, I'll do it manually. But again, we go back to number of protons, number of neutrons. There's a lot of information here. So I'm going to show you the temperature evolution as a function of time. As the material expands, of course, adiabatic cooling takes place and the temperature decreases. The density decreases very dramatically. And in black is actually show the heating rate from our process nucleosynthesis. So this is the decay heating rate, and this is ultimately what's going to power the light curve. You see here temperature, density, heating rate, and you see YE. YE is the electron fraction, which in the absence of pairs is the proton to neutron ratio, which is 1/10. That means that this material has basically 1 proton for every 10 neutrons. This is incredibly important because in nuclear statistical equilibrium, you can immediately see that you have tons of neutrons, but you also already have some heavy elements. So in nuclear statistical equilibrium, at these densities and temperatures and basically composition, you already have the nuclei to start capturing the neutrons. So when you look at the abundance pattern, when the material is incredibly neutron rich, you clearly see already elements in the first peak being formed. Yeah, and this is basically as a function of time, and we're following the evolution of the tidal tails. So you see you're capturing very, very far off equilibrium. You cross the first, second, and third neutron closed shell, and then you decay back to stability, and you immediately see how the peaks basically shift to the left. So you get first peak, second peak, and third peak, and as a function of time, this decay continues, and it's ultimately basically powering the heating rate as a function of time. No? And this was incredibly important. These are calculations by my former grad student, Luke Roberts, that made these publicly available in the SkyNet network with Jonas Lippener. And the decay continues. But of course, as you're close to stability, the position of the peaks don't change. So let me give you a feeling of how much gold, just to wake you up, how much gold these neutron star mergers make. The answer is about a Jupiter mass of gold. Yeah. So that's 10 to the 30 grams, and I guess 1 gram is 10 pounds, so 10 to the 31 pounds. Very rich event. If this is not impressive enough, this is about the amount of gold stored in about 1 million stars. Yeah. So immediately you see that one of these events, even though it's rare, can supply a significant fraction of stars with the total R process needed. And this is going to become central to the discussion that we're going to have about chemical evolution. Okay, so just to summarize, we have these, in this particular case, 2 objects. It can be a black hole and a neutron star, or 2 neutron stars. They evolve through the emission of gravitational waves, which carry both energy and angular momentum for hundreds of millions of years, if not gigayears. You become dynamically unstable. You have this unbound debris. In a few milliseconds, you produce the R process. Yeah. You start decaying, so you expand, but you have nuclear decaying of the outflow, but you're optically thick, so you retain that heat. You continue to expand and adiabatically cool until you start becoming transparent. And once you become transparent, you start actually seeing light from this material. So I'm going to guide you through kind of what are the observational signatures of that light, and how can we infer that our process nucleosynthesis actually took place. So what I'm showing you there is the equation evolution of the internal energy as a function of time. My pointer doesn't work. So the first term is the adiabatic cooling. The second term is basically the transport. Yeah, both are negative because they're basically decreasing the total energy density. Diffusion, ultimately, the diffusion time is really important. And ultimately, what's basically keeping the temperature is the nuclear heating term. Yeah? So what I'm showing you there is the evolution of the nuclear heating rate as a function of time. And as actually inferred by Lee and Paczynski, they basically argue that at a given time, there's so many elements that are decaying that you're likely to get a power law. And what I'm showing you there is basically the contribution of a particular element to the decay. So you can see at a given time, there's so many nuclei that are decaying and contributing to the decay. Now, getting an understanding of the heating rate is essential because that's ultimately captured by the light curve. So let me give you an insight as to why. So if we look at the standard type 1a supernovae, this is basically, and what I'm showing you here is the total bolometric light curve. Yeah? So ultimately, you're doing calorimetry of your energy injection rate. And then as a function of time, in the type 1a model, you have basically nickel 56 decaying to cobalt 56, which takes about 9 days, and then ultimately to iron 56. And what you see there in the dashed line is actually the heating rate, and what you see in the solid line is actually the light curve. So ultimately, the bolometric light curve follows the heating rate at late times. And the kilonova models, and they were named kilonova because they're about 1,000 times brighter or more luminous than a nova. Those are the ones from neutron star mergers. And as you can see, the late time bolometric luminosity follows the heating rate. So that was the first signature that we were looking for, that the light curve will decay with the power law that was inferred from our process nucleosynthetic decay. And these systems are also much less brighter. Why? Because they have much less mass, ejecta, so they become optically thin early on. And of course, the heating rate per unit mass of the R process is smaller than the heating rate from nickel to cobalt to iron. So in general, these light curves are difficult to detect. These transients are difficult to detect, not only because they're dim, but as what I'll explain to you, they're also red. And as you know, or detection capabilities in the infrared are not as effective. Now, something that was pioneered by Dan Kaysen is to really understand what is the atomic structure of our process nuclei. Yeah, what I have guided you through is basically the nuclear structure, but the atomic structure is incredibly important because you have a ball of very heavy elements, and the question is, what is the optical depth to the photons? What does the photons see? And basically the opacity of these nuclei depends on the many ways that you can rearrange the valence electrons. And of course, the most complex nuclei are the F-shell nuclei, yeah? Because they have so many ways in which you can actually arrange the valence electrons that they have the most complex atomic structure. And these nuclei, both the lanthanide and the actiniide series, fall between the second and third peak. So if you produce the heavy R process, you're going to have these nuclei. Now, to give you a feeling of just their complexity, here if you compare, say, an iron nuclei, which is not an F-shell nuclei, with an F-shell nuclei, you can see that these nuclei in the periodic table, the lanthanide and lactidines, have about a factor of 10 times more lines. You can see iron has hundreds of thousands of lines, but these other nuclei have millions of lines. So they're atomically much more complex, and as a result, they produce significant opacity at infrared wavelengths. Here is the D-shell opacity compared to the lanthanide opacity, and one of the predictions was that the light had to basically degrade to infrared wavelengths in order to escape. Yeah? And this is basically an example of a radiation transport calculation changing the F-shell nuclei fraction. So if you have material with basically only first peak elements, you can see it's very bright in the optical. And as you increase the proportion of second and third peak elements, the spectrum becomes incredibly red. And that was the prediction, that if you have produced second and third heavy R process, you will basically see a spectrum that it's incredibly red. Now, I don't want you to be kind of misguided by those wiggles, because the way that you should think about it is you have millions of lines, you're moving at a fraction of the speed of light, so every one of those lines is broadened. So what you're seeing is edges of a multitude of lines contributing to the opacity of that wavelength. And one of the reasons why also the spectrum provides information is because of the broadening of the line. So you can see here depending on the expansion velocity, you can actually tell the expansion velocity simply by looking at the overall broadening of the spectrum. So that's another way in which we're able to independently characterize the expansion velocity of the ejecta. So, August 17, 2017 happened. We saw these two, neutron star merging as a function of time, and we basically desperate went and searched for the electromagnetic transient. I was incredibly lucky to be part of the 1 meter to hemisphere collaboration. Astronomers were not very inventive. We have 2 1 meter telescope, one in Lick Observatory, one in the south in the Swope in Chile. And for reasons that I will keep brief, we were the first team to actually detect the electromagnetic counterpart associated with the gravitational wave signal. I'm proudly the oldest individual in that plot, in that picture, and we had an incredibly early career team. And Dave Coulter there with I Want to Believe t-shirt was the one that actually made our team be successful. Why? Because with a 1 meter telescope, we were competing with 4 meter telescopes. And rather than tiling the entire sky, basically what we did is we just target the galaxies. And we made an algorithm in which we just target the most massive galaxies in the field. And as a result, by about a minute, we beat the 4 meter telescopes in detecting the electromagnetic transient first. So this is what we saw. Initially, we saw a blue peak that then faded to infrared wavelengths, as expected if you had produced these heavy R processes. So, just based on calorimetry, if you actually think about the bolometric light curve, you can clearly see that the bolometric light curve follows the heating rate fairly effectively. There are, of course, issues in trying to do corrections of the bolometric light curve at late times where the host galaxy actually makes a contribution. But in this simple calculation, you said that the minimum amount of mass that you require in order to produce the total amount of energy in light that you saw was about 0.02 solar masses. Again, this magic number of 10 to the minus 2 multiplied by the rate of 1 per 10 to the 5 years. Now, we had to make corrections in seeing how efficient the thermalization takes place. And the current estimate is that factor of 3. So we probably require 3 times as much mass as what's inferred from that. So the assumed LIGO rate at this particular time implied 25 mergers per mega year. Again, 10 to the minus 5 per year per galaxy. Our estimates for this event is that the average total R process mass is about 0.06 per event. And that means if every single neutron star merger will produce about the same amount of mass, you get that in our galactic history, we have about 10,000 solar masses. So enough to actually supply every single star with the R process mass that it's currently observed. Incredibly surprisingly, our fits to the spectrum are actually relatively promising. And this becomes actually more surprising because we don't actually know the oscillation strength and the energy of every particular line. We just treat them statistically. Yeah. So the fact that we get a relatively qualitative description of the spectrum is important. And what we saw at late times is that you needed this red component, that you have indeed produced basically material in the second and third peak, because that's where these very atomically complex nuclei lie and allows to give a reasonable description to the spectrum. So this is the model, broadly speaking, that we came up with. The two objects come together. They get these squeezed polar ejecta. The squeezed polar ejecta is not very highly neutron rich. You're only able to produce the first peak. So you get a blue first peak. And then either the tails or the nucleosynthesis in the accretion disk, which is much more spherical, give rise to the redder component at late times. Yeah, and bolometrically speaking, and in terms of broadening colors, you get a reasonable description of the data. So this event was incredibly exciting for many reasons, but hopefully I'll convince you that there's clear evidence that for the cosmic creation of heavy elements via neutron capture, both because of the bolometric light curve following the decay that we expected and the spectral characteristics that we saw. Now, our search continues. I wanted to kind of highlight that LIGO is detecting a lot of neutron star black hole mergers. One of the challenges there is that if the black hole is actually very massive, the neutron star gets tidally disrupted inside the event horizon, and you don't expect to have any mass ejection. So where it says no disk, it means that you don't expect to see any mass ejection. What that plot shows you is basically the ratio of the black hole to the neutron star as a function of the spin of the black hole. The faster the black hole is spinning, the easier it is for material to be ejected. So it aids. But these are sort of three events that I showcase here. The most promising one, GW200115, gives you constraints around here. So when we're searching for these events, we don't know exactly if these events actually produce an ejected material or not, given the uncertainties. But I just wanted to give you a feeling of how incredibly challenging it is to actually search for this event. So on the left side, it's about 100,000 hours of follow-up observations for this particular event. And you can see that our upper limits at those distances don't even get to kind of the blue kilonova or red kilonova components there at the bottom. If you had a short gamma ray burst of axis and afterglow, we should be able to see it because those are incredibly bright. But just seeing the kilonova itself is actually being challenging. And the position uncertainty have been currently not very good in order to continue to search for these events. Okay, I'm going to transition to kind of the last part of my talk, and I want to give you a feeling of why these elements are essential to life. And it's ultimately linked with the production of the magnetic field, which is shown here by a beautiful simulation of Jerry Glassmeyer. So I'm going to guide you through a very simple chemical evolution model. So imagine that you have something like magnesium that it's producing type 2 supernovae. So type 2 happens very often and produces a little bit of mass of magnesium. So I want you to think about a chocolate cookie with a very thin layer of chocolate that it's actually well distributed across the cookie. So that means that you don't expect large variations within the disk of magnesium. But if you think about europium, I want you to think about a chocolate chip cookie, where all the chocolate is basically concentrated very locally. And that means that if you're born with material close to the chocolate chip cookie, you will have a huge amount of our processed material. And if you're far away from the chocolate chip, you will have little. And ultimately, that's what we see. What we see is that the RMS variations of magnesium to iron are small. And in fact, there's current amount of debate as to whether those variations are systematic or intrinsic. But the variations of europium are incredibly large. And what we think is that that envelope, as a function of time, is actually turbulent mixing, efficiently mixing the R process nucleosynthesis. So if you have a supernova explosion today, by the time you get to the cooling mass, the total amount of iron that it's injected into the interstellar medium is negligible. One supernova remnant doesn't increase. But if you have a neutron star merger today, by the time you get to the cooling mass, you're going to have a significant enhancement compared to even solar metallicity. So these events produce a huge amount of mass per event. So we have tried to do these both at the cosmological scale. There's some things that you have to assume at the cosmological scale because you're not resolving the cooling mass. So in order to resolve the cooling mass, you have to do this gas interaction in small patches of a galaxy where you're resolving each individual supernova remnant and trying to think about how mixing takes place. So I'm just going to kind of illustrate to you that in these simulations, you actually capture exactly what we're talking about. In red is basically the iron production from core collapse supernova, and as you can see, they happen very often. They produce little material, so the RMS fluctuations of iron is actually small, while europium gives you these very, very large variations that take significant amount of time to turbulently mix as you inject more and more material. And in fact, you can put a constraint of basically the rate of injection just solely on turbulent mixing. So we've done that for Milky Way progenitors or satellites, and you get a constraint that the amount of mass that you have to inject is actually not 10 to the minus 7, but about 10 to the minus 6 solar masses per year. Why? Because a significant fraction of the R process is actually ejected in the wind. Yeah. What the cosmological actually simulations are telling us is that the intergalactic medium actually should be highly enhanced of R process nucleosynthesis because neutron star mergers happen farther away in the galaxy and that material gets ejected preferentially. So I wanted to kind of continue this RMS variation at low metallicity all the way to today. So what I wanted to highlight here is that just the RMS fluctuations alone tell you that these events have to be rare and that turbulent mixing has to operate relatively inefficiently because the rate of these events is small, while turbulent mixing is very, very effective for just, say, oxygen or magnesium coming primarily from core collapse supernovae. At some point in time, which it's to be debated, you start being able to produce, have enough metals to produce planets. So solar systems basically give rise. And, ultimately today, you still have a variation of our process content of about a factor of 3 observationally. So why is this important? Why is this crucial for habitability? So this is the question that we attempted to address. And the reason why this is incredibly important is because uranium and thorium are the primordial elements that are heating the interior of the Earth. Why? Because they have decay lifetimes that are long enough that are basically prevalent today. If you look at that plot, aluminum-26, of course, was incredibly important early on, but in today's Earth, the vast majority of the heating rate is actually uranium and thorium, which are basically heavy R process. And in fact, they think that they're more important than potassium-40 simply because when the Earth was molten, both uranium and thorium was actually able to get into the core by gravitational settling much more effectively. So then the question is, well, what happens if we vary the energy generation rate in the interior of the Earth by a factor of 2 or 3? And that's sort of the question that we attempted to address. And one of the reasons, if not the most important reason, is that this heating rate basically modulates the fluid convection motions on Earth. And if you want an effective alpha omega formalism to be effective in the Earth to build a magnetic field, the strength of the convection motions is incredibly important. So in this paper led by Francis Nemo, we basically argue that if you have significantly more, and by significantly more, we made a factor of 2 more R process element that our sun, you will have significantly radiogenic heating, you will have extreme volcanism, but you will not be able to have a magnetic field or the dynamo operating effectively. Yeah, and of course, we think that those sort of planets are not habitable. And of course, if you have less, the alpha omega formalism operates very effectively, but you will have less radiogenic heating and the planet is likely to be geologically dead. So then the question is, being geologically dead important or not for life? So we think that in the Drake equation, there should be another term that tells you what is the fraction of our process that you have simply because they're modulating the energy generation rate in the interior. Okay, so hopefully I'll convince you that these neutron star mergers are exciting from the perspective of gravitational waves, from the perspective of heavy element nucleosynthesis, that there's lots of exciting things that you can infer from the light emission that you see from these objects, and that ultimately how those objects are mixed into the interstellar medium and form new stars may be essential for habitability. And I'll stop here and thank you for your time.